When a satellite orbits in a circular path, then its acceleration is centripetal, meaning it doesn't correspond to a change in speed, just a change in direction. And that centripetal acceleration is acceleration caused by gravity, and the acceleration due to gravity is the same as the gravitational field strength. Now, gravitational field strength is not uniform for any planet. It has a particular value at the surface, but as you go to higher elevations, that gravitational field strength drops off. So we want to make a graph of what it looks like, how rapidly field strength drops off with increasing altitude, which corresponds to a graph of how does the centripetal acceleration of a satellite drop off with increasing altitude. So here's an equation we've seen before. The product of G and M appears again and again in a lot of the equations we have. So for the Earth, let's see if we can come up with just a numerical value for the product of G and M. It's 6.67 times 10 to the negative 11th, multiplied by the mass of the Earth, 6 times 10 to the 24th kilograms. This comes out to very nearly 4 times 10 to the 14th. I'll leave it up to you to decide what those units are equal to. Now, if we wanted, we can then make a graph using this equation and reduce it a little bit. Say centripetal acceleration is equal to 4 times 10 to the 14th divided by r squared. And we could let r be some value in meters. However, it might be more useful, instead of expressing r in terms of meters, to express it as multiples of the Earth radius. So if that's the case, it would be multiples of the numerical value 6.4 times 10 to the 6th. So we could have centripetal acceleration is 4 times 10 to the 14th divided by 6.4 times 10 to the 6th x quantity squared. Of course, when you work this out, you just get centripetal acceleration is equal to 9.8 over x squared. So if we let x equal 1, then we mean 1 Earth radius. If we let x equal 2, we're talking about 2 Earth radii, 3 Earth radii, 4 Earth radii, and so on. And we know there's no point in graphing within the shaded area. So for orbital radius equal to 1 Earth radius, we're talking about a treetop orbit, and then we would have 9.8 divided by 1 squared, which obviously gives us 9.8. So there's one data point. For x equals 2, so for 2 Earth radii, then we get 9.8 divided by 4, gives us a value of about 2.5. When x equals 3, centripetal acceleration would be 1.1, and so on. So when trying to eyeball this graph by hand without the use of graph paper, then all these data points I'm constructing are just rough estimates. If we connect the data points, we know we're going to get a graph something of this shape. So if you want to see it graphed exactly, you could either grab a piece of graph paper and try it yourself, or I'd encourage you to check out a free graphing software called Desmos if you're not already familiar with that. You can use Desmos online, or you can download an app. So we look back at our equation, we're really graphing centripetal acceleration on the y-axis. So this formula is consistent with the formula y equals 9.8 over x squared. So all you have to do in Desmos is enter the formula y equals 9.8 divided by x squared. if we zoom in, we can see for 1 Earth radius, let's look at our graph. Here we go. When we're at a radius of 1, we have an acceleration 9.8. The radius goes to 2. The acceleration is about 2.45. When we go to 3 Earth radii, we have an acceleration that rounds up to about 1.1 meters per second squared. 4 Earth radii, and so on. What about a graph of velocity, tangential speed versus orbital radius? So again, we can make the substitution for gm, call it 4 times 10 to the 14th. Then we could also make the substitution, say r is equal to multiples of Earth radius, or in other words, r is equal to 6.4 times 10 to the 6th times x. So I encourage you to make a graph using Desmos of y equals the square root of 4 times 10 to the 14th over 6.4 times 10 to the 6th x, and see what that graph looks like. You should get for 1 Earth radius a value of about 7,900 meters per second. And then as you go to 2 Earth radii and 3 Earth radii and 4 Earth radii and so on, what does that graph look like? You could do the same thing for the equation that expresses period as a function of orbital radius. Now, we don't want to express period in units of seconds because that's hard to relate to. So if you want the period in hours, then you'd have to divide both sides of the equation by 3,600 seconds per hour. So we could make some substitutions. Call this 2 pi divided by 3,600 times the square root of 6.4 times 10 to the 6th x cubed divided by 4 times 10 to the 14th. I've already programmed this into Desmos, so let's take a look at what that graph's going to look like. Well, first of all, let's set it up here as multiples of Earth radii. See, with this graph, there's a special point to look for. If we scale this correctly, we know that for a treetop orbit, when the orbital radius is the Earth radius, then you have the lowest possible period of orbit that's equal to about 90 minutes, or we can call it 1.5 hours. And the graph should be a concave up curvature from there. And what we'd like to find is somewhere up the scale, if I can make a scale break here, there should be a data point that corresponds to 24 hours. What's the orbital radius in that case? So here I've programmed it. You can take a look at the formula that's indicated. I believe that's exactly the formula I was talking about. 2 pi over 3,600 times the square root of 6.4 times 10 to the 6th x. All of that's cubed divided by 4 times 10 to the 14th. And you can see on the right the corresponding graph. Now from 0 up to 1 Earth radius, none of this data is meaningful, but right at 1 Earth radius we get about 1.4, not 1.5 hours, but close. For 2 Earth radii, the period would be about 4 hours. For 3 Earth radii, the period would be a little over 7 hours. On and on we go. So let's see if we can figure out what radius would give a period of 24 hours. Getting close. Closer, There we go. About 6.6 Earth radii would correspond to an orbital period of 24 hours. So we say that's the orbital radius for a geosynchronous satellite. Let's double check that numerically. Period is 2 pi times the square root of r cubed over gm. So that means period squared over 4 pi squared is r cubed over gm. This means r is the cube root of gmt squared over 4 pi squared. So the orbital radius for a geosynchronous satellite of the Earth is the cube root of 6.67 times 10. Well, I don't need to write that all individually. I know what the product of gm is equal to. 4 times 10 to the 14th. Period is 24 hours, but I need to multiply that times 3,600 seconds per hour. It's t squared divided by 4 pi squared. So we're talking about taking the cube root of 7.56 times 10 to the 22nd and this comes out to a value of r equal to 4.23 times 10 to the 7th meters. It's a big distance, can't relate to that, but I know the radius of the Earth is 6.4 times 10 to the 6 meters, so if I divide, I could express the orbital radius for a geosynchronous satellite as multiples of Earth radius, and I get, indeed, 6.6 Earth radii. If that's supposed to represent the Earth, and that's supposed to represent the Moon, then my figure is way out of scale, because, as I've mentioned before, the distance between the Earth and the Moon is 60 times the radius of the Earth. So it's hard to properly draw it to scale on any piece of paper without making either the Moon or the Earth look too small. In any case, if you were to travel away from the surface of the Earth toward the Moon, how far along your journey would you have to go before you encountered any geosynchronous satellites? So, the distance between the Earth and Moon is 60 Earth radii, but the distance for a geosynchronous satellite is equal to 6.6 Earth radii, which means it would be an altitude from the center of the Earth, it's 6.6 Earth radii. But from the surface of the Earth, it would then be 5.6 Earth radii. So it's pretty far. I guess it represents roughly 10%, a little more than 10% of the distance to the Moon is the distance to a geosynchronous satellite. These geosynchronous satellites are used in telecommunications. It's very convenient to keep a satellite parked over one spot of the Earth if you want to make a broadcast to a certain region. So large part of what we pay for, whether we use maybe DirecTV or Dish TV, or maybe you pay for Sirius XM radio in your car, or certainly for your cellular phone, a lot of the payment is to afford for them not only putting the satellite up into a geosynchronous orbit, but maintaining that satellite's orbit. Without it, we don't have any satellite communications.